Here we have three solutions of salts which will have a significant pH based on one of their ions. Let's look at part A to begin with. The ions present within potassium nitrite are, of course, potassium ion and nitrite ion. To figure out which ion or ions are important, we have to think of their conjugates. For the positive ion in a salt, you're always thinking, if it's a conjugate acid of something, what would that something be? And would it be a strong or weak substance? Well, in the case of metal ions, they're never important unless their charge is 3 or higher. Well, potassium is a metal whose charge is a 1+, and that certainly doesn't mean that it's high enough to make a difference. Let's look at the negative ion. Nitrite is the conjugate base of something. We'll figure out what that thing is and then ask ourselves whether that thing is strong or weak. If it's weak, then the nitrite ion is important in determining pH. If it's strong, it's not important. So nitrite would be the conjugate base of something. To figure out what it's the conjugate base of, you would add a proton to it. Well, that makes it HNO2. HNO2 is nitrous acid, not nitric acid, but nitrous acid, which is a weak acid. That means that NO2 minus is the important ion for this salt. If NO2 is the important ion and it's a conjugate base, then we're going to write a base dissociation equation. Following the format of any base dissociation, we need water as one of the reactants. We'll produce hydroxide and the conjugate acid of the base. We'll make an ice table with this. The pure liquid, water, drops out, and we'll refer to what the problem gave us for the initial concentration of 0.1 molar. They don't mention any hydroxide or nitrous acid to begin with, so we shift to the side with the zeros. And once again, since we have a base dissociation equation, we need a Kb value. Well, you can't look up a Kb value for nitrite ion. Instead, we're going to have to find the Kb value by taking Kw divided by the Ka value for its conjugate, nitrous acid. We can look that one up. And you would actually have to look in Appendix 5 in your textbook, or of course you could Google this. The Ka value for nitrous acid is 4 times 10 to the negative 4th. And if you divide Kw by that number, you get 2.5 times 10 to the negative 11th. Now we have a Kb value that we can work with. And we've got our ice table. Product concentrations are X and X, and the reactant concentration is 0.1 minus X. So it's product concentrations over reactant concentrations. We're certainly okay to make the mathematical assumption in this case because of the size of the K value. It's really, really small at 10 to the negative 11th. So we're going to go ahead and make the assumption that the quantity 0.1 minus X is roughly just 0.1. When you crunch that on your calculator, we get X equal to 1.58 times 10 to the negative 6th. And in our ice table, the value of X at equilibrium is equal to the hydroxide concentration. So from that we can do a pOH calculation, taking negative log of hydroxide, and then we'll subtract from 14 to get pH. That one works out to be 5.8. pH then would be 14 minus that number, and gives us 8.2. And that would be our final answer for part A. Moving on to part B. B is going to be really similar to part A because once again it's the negative ion that's important. Let's list the ions. Within sodium hypochlorite we've got Na+, and the other ion is hypochlorite, OCl-. Metals are never important unless their charge happens to be 3 or higher. And the reason for that is their conjugate would be something strong. The negative ion, however, let's take a look at this one. For negative ions, we always picture it as a conjugate base. It's a conjugate base of something. Well, that something we can find by adding an H to it. HOCl, hypochlorous acid. That is a weak acid, and that means that the negative ion is important in determining pH. So once again, like in part A, it's the negative ion that is important. Since we have a conjugate base that is important, we write a base dissociation equation for it using the standard format, which requires water as a reactant. We produce hydroxide, and we have a conjugate acid at the end. We'll make the ice table. Water drops out of the ice table because it's a pure liquid, and we'll pull the initial concentration of 0.45 that they had given us as the initial concentration of hypochlorite, and flesh out the ice table, shifting to the right. And we need because this is a base dissociation, we need a Kb value. Well, you can't look up a Kb value for hypochlorite ion. Instead, you have to calculate it from Kw. For any conjugate acid-base pair, Ka times Kw, Ka times Kb equals Kw. So that means Kb equals Kw over Ka for the conjugate. Well, we can look up the Ka for hypochlorous acid, HOCl, in any table in your textbook, or online would be fine too. So you could either look Appendix 5 or Table 14.2 in your book, but we need to get the Ka value for HOCl in order to complete this calculation. When you do look that up, we get 3.5 times 10 to the negative 8th. And Kw divided by that gives us 2.86 times 10 to the negative 7th for the value of Kb. Now we can use that value in our ice table. Product concentrations over reactant concentrations. So we've got X, X, and the quantity 0.45 minus X. Since the value of Kb is quite small, it's on the order of 10 to the minus 7th, I can guarantee you that we're okay making the mathematical assumption that the quantity 0.45 minus X is roughly equal to 0.45. When we go ahead and solve that, X works out to be 3.56 times 10 to the negative 4th. Okay, In the ice table, X was the hydroxide concentration. So we can find pOH by taking the negative log of the value of X, 3.56 times 10 to the negative fourth. If you negative log that, we get 3.45. And then pH would be 14 minus that number, which works out to be 10.55. Notice that for both parts A and B of this problem, the pH in the end worked out to be above 7 because it was the negative ion that was important in determining pH. Therefore, we call those salts basic salts. Salts which produce basic solutions or solutions with a pH above 7. In part C, it's going to be the opposite. Let's take a look at that one next. Oh, I didn't want to do that. Here we go. Okay, so part C, we have 0.39 molar ammonium perchlorate. I'm going to move this business out of the way and we'll just start fresh at the top here. Okay, so part C, they gave us 0.39 molar ammonium perchlorate. Let's list the ions that are there. Ammonium ion, of course, and good old perchlorate. This time, the conjugate, the positive ion does have a proton in it, so we can think of its conjugate. So the positive ion is the conjugate acid of something. The negative ion would be the conjugate base of something. We'll list both those things and determine whether those things are strong or weak. So if NH4 is the conjugate acid of something, mentally I'm subtracting an H from its formula to give it NH3. NH3 is the classic weak base. For the perchlorate ion, ClO4, we're saying it's the conjugate base of something. Mentally, I'm adding an H to get perchloric acid, which, of course, is one of your 7 strong acids. The ion that came from a strong species is not important in determining pH. This ion that came from a weak species is important. So unlike in parts A and B, in part C, the positive ion is important. And since we have a conjugate acid, we'll write an acid dissociation equation following acid dissociation format. So we take NH4, draw an arrow, and show it kicking off a proton and becoming NH3. We'll ice that down. And in the problem they gave us 0.3 molar initial concentration. We'll shift to the right. Now, do we have a Ka for ammonium ion, the NH4 ion? Not necessarily. Actually, you could look this one up in the Ka values in table 14.2. But let's say you couldn't. If you couldn't, you would have to calculate it from Kw. And for any conjugate acid-base pair, Ka times Kw, Ka times Kb equals Kw. So Ka could be found by taking Kw divided by Kb for the conjugate. Kw, of course, is the ion product constant for water, 1 times 10 to the negative 14th. And if you looked up in either Appendix 5 or Table 14.3 in your book or online, you could find the Kb value for ammonia. It's 1.8 times 10 to the negative 5th. And if we work that out, it's 5.6 times 10 to the negative 10th. Now we have a Ka value that we can work with. So for this ice table, Ka is 5.6 times 10 to the negative 10th. We'll take product concentrations at equilibrium all over reactant concentrations at equilibrium. And because of the size of this K value, we're guaranteed to be fine when making the mathematical assumption that the quantity 0.39 minus x is roughly equal to 0.39. When we crunch the numbers and find x, we get 1.47 times 10 to the negative 5th. And if we look back at our ice table, x is the equilibrium concentration of hydrogen. So this time, to get pH, we just take negative log of x, which is 1.47 times 10 to the negative 5th, and that works out to be 4.83. You don't need to subtract that number from 14, because in this ice table we found hydrogen concentration directly, whereas in the previous two ice tables, in parts A and B, we found hydroxide concentration at equilibrium, and from that found POH, and then needed to subtract from 14 before we could get pH. With an acid dissociation, it's a little bit more direct. Notice that in part C, since the positive ion was important in determining pH, we ended up with a pH below 7. It's an acidic salt.